Mbak Zuli atau Bu Nari mungkin bisa dimulai terbuka sekarang.
Apakah sudah bisa kita mulai?
Sudah.
Oke. Assalamualaikum warahmatullahi wabarakatuh. Good morning, ladies and gentlemen. We delighted to welcome you to the first JESSD Symposium, International Symposium of Earth Energy, Environmental Science and Sustainable Development on special issue, cutting-edge research on earthquake and tsunami monitoring and mitigation. Today's event is a joint session of School of Environmental Science, University of Indonesia, and the Center of Research and Development BMKG. Before we proceed the program today, we would like to express our sincere gratitude to the Honorable Vice Director of School of Environmental Science, University of Indonesia, Mr. Triedi Budi Susilo, Director of Research and Development BMKG, Mrs. Nelly Floridariama, Mrs. Karen Litgu from Earth Observatory of Singapore, Mr. Walter Dimuni from US Geological Survey, Professor Wijojo Adiprakoso from Faculty of Engineering, University of Indonesia, Professor Raldi Hendro Kustur from School of Environmental Science, University of Indonesia, Mr. Supriyanto Rohadi from Center for Research and Development, BMKG. And also we welcome all the participants of the first JESSD Symposium. For a brief moment, we would like to invite you to rise and sing Indonesian anthem, Indonesia Raya. May all we rise. Have a seat. Thank you for the attention. Distinguished ladies and gentlemen, we are going to the opening remarks. For the first speech will be given by Director of Research for Research and Development Center, Mr. Nelly Floridariama. Mrs. Nelly, the time is yours.
Assalamualaikum warahmatullahi wabarakatuh.
Assalamualaikum.
May prosperity be with you all. Honorable Dr. Triedi Budi Susilo as Vice Director of School of Environmental Science, Universitas Indonesia. Our, our speakers, Professor Walter Mooney from USGS USA, Dr. Karen Litgo from Earth Observatory of Singapore, Professor Wijoyo Adi Prakoso, Head of Geotechnical Engineering Laboratory, Universitas Indonesia, Dr. Supriyanto Rohadi from BMKG, and also for our moderator right now, Dr. Raldi Hendro Kustur from School of Environmental Science, Universitas Indonesia. Distinguished participants, ladies and gentlemen, first I would like to extend a warm welcome to all participants of the symposium and also special respect to the School of Environmental Science, Universitas Indonesia for the efforts and cooperation with BMKG in preparing and organizing at this first GESSD symposium on this special session, Cutting Edge Research on Earthquake and Tsunami Monitoring and Mitigation. Distinguished participants, ladies and gentlemen, earthquakes are among the most destructive of natural disasters. This disaster poses a great threat because it occurs erratically and the consequences are unpredictable. Earthquakes can trigger many disasters such as tsunamis, liquefaction, landslide, eruptors, and also ground shaking. This is also one of the biggest threats to natural disaster in Indonesia. Our country is at the meeting point of three major continental plates, the Pacific, the Eurasian, and the Indo-Australian plates, and the much smaller Philippine plate. It also falls on the Ring of Fire, a horseshoe-shaped area around the edge of the Pacific Ocean from Australia to the Andes, along which 90% of all earthquakes occur. In late 2018, Indonesia was hit by two destructive tsunamis, which challenged our understanding of tsunami hazard, warning and response mechanisms. The first event was the Palu and Donggala tsunami of 28th of September 2018. And the second was the Sunda Strait tsunami of 22nd of December 2018, following an eruption and partial collapse of the Anak Krakatau volcano. Earthquakes can cause damage to facilities or infrastructure, casualties and injuries, and disrupt the socioeconomic function of the affected areas. Usually, the effects will rise significantly as a result of increasing in population and structures or infrastructure facilities. Although it is impossible to prevent earthquake from occurring, it is possible to mitigate the effects and to reduce loss of lives, injuries, and damage. Many research is being conducted right now to the most appropriate and applicable solution for the mitigation of adverse effects of earthquake and tsunami. In order to minimize the impact of disaster, it is necessary to make early and optimal mitigation effort with more intense geoscience research, installation of representative and up-to-date monitoring networks, and information dissemination. Ladies and gentlemen, through decision at the first GESSD symposium, we will share and discuss the latest research from earthquake and tsunami expert. Uh, I have mentioned there are four speakers right now that we have. So concluding these remarks, I would like to express my appreciation and gratitude to all those who have contributed to making this event a success as expected. Thank you for your kind attention. Stay healthy, stay strong, and stay united. Wassalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam.
Thank you, Mrs. Nelly. We are going to listen the second speech, opening remark from School of Environmental Science, University of Indonesia, delivered by Vice Director of School of Environmental Science, Mr. Triedi Budi Susilo. Mr. Budi, time is yours.
Yeah. Thank you. Assalamualaikum warahmatullahi wabarakatuh. Good morning, ladies and gentlemen. Before we start our event, I would like to send my deepest condolence to our brothers and sisters who have passed away as victims of COVID-19. Our sincere prayers to the bereaved families with these sad turn events during the pandemic crisis. The first GESSD symposium will soon conclude. It is our great honor to spend the past 3 days with friends from different countries. At the opening session, I said that I hope we would learn new ideas from each other, which we could adopt to further improve our work in this important area. I know that there have been many interesting and useful presentations these 3 days for webinars, parallels, and poster sessions. With your participation, the symposium successfully finished all its sessions. On behalf of the School of Environmental Science of Universitas Indonesia, I sincerely thank Bank Rakyat Indonesia, Unilever, and PT Larus Birus Utama for sponsoring this event and for APIKI Indonesia Network and BMKG. I'm proud of all keynotes, committees, and reviewers for their time and hard work to run this event the best they can do during this challenging time. We discussed oil palm, waste management, environmental technologies, disaster management, and sustainable development to be more balanced for efficient, greener, and most of all, for a better future. As the symposium ends, I believe we all have the same feeling that people are persistently exploring the dream of sustainable development. During these 3 days, we see the possibility that dreams become a reality through collaboration and exchanging knowledge between representatives of governments, researchers, industry associations, and NGOs. I hope that all experts and representatives present at this symposium can enhance friendship and strengthen cooperation so that we can join efforts in pushing forward the sustainable development. In this event, I would also like to announce a piece of exciting news. Next year, the School of Environmental Science Universitas Indonesia will open a Master's in Disaster Management. We look forward to meeting you again at our next fruitful event. To close this event, I would like to quote by Sir David Attenborough: "Cherish the natural world because you are a part of it and you depend on it. Stay safe and healthy. Thank you. Wassalamualaikum warahmatullahi wabarakatuh."
Waalaikumsalam. Thank you, Mr. Budi. Distinguished ladies and gentlemen, we shall begin the plenary session, Cutting-Edge Research on Earthquake and Tsunami Monitoring and Mitigation. This session will be moderated by Professor Raldi Hendro Kustur. I will hand over to Professor Raldi as moderator of this session. Please,
Okay.
Professor.
Okay. Very good morning to all of you. Excuse me, I have to check whether the speaker is working or not. Is it working?
Yes.
Yeah, it's working now. Okay. Today, we started with the cutting-edge research on earthquake and tsunami monitoring and mitigations. For this first session, we have Professor Wijoyo Adiprakoso, and the second with Dr. Karen Litku. And perhaps the committee can help me with the short biodata for Professor Wijoyo. Masangga, please, to share the screen of biodata of Professor Wijoyo Adiprakoso. I think Professor Wijoyo coming from the Department of Civil Engineering, Faculty of Engineering, Universitas Indonesia. The monitor, I think, is it on now? Yes, okay. And the second is Dr. Karen. She's from Earth Lab Observatory of Singapore. And she holds a PhD from University of Cambridge. And then currently she's working with study of Lombok, the one that you mentioned before, Dr. Karen. And we started with Professor Wijoyo with, can you share the slide, Mas Angga? The topic would be earthquake disaster mitigations on infrastructures. Professor Wijoyo, perhaps this time is yours. And we have about 15 minutes to talk, and straight coming to Dr. Karen later for the second topic. Please welcome your time, please.
Okay, thank you very much, Professor Kostur, for a nice introduction. Good morning, everyone. My name is Wijoyo Prakoso. As mentioned, I am a professor at the University of Indonesia in Civil Engineering Department. And this morning, I was asked to present some overview what we have in Indonesia in terms of earthquake mitigation. And my specific topic for this presentation is advances and challenges in earthquake geotechnical or civil engineering research in Indonesia. And the outlines of these presentations are as follows. I'm going to talk about the general overview of what we have at present. And then we are going to talk about some details about the what we have done for the transient ground motions, the permanent ground deformations. And as we civil engineers deal with structures, I'm going to touch upon some structures research and what we are doing right now. And I'm going to conclude with some closing remarks. And when we talk about what we have now, we actually are quite advanced in terms of building codes. For example, we just recently updated our building codes for the earthquake resistance building code. This is so-called Standard Nasional Indonesia, SNI, Indonesian National Standard, 1726, 2019. Basically, this is the basics for designing all the building structures in Indonesia. We adopted basically this SNI from American Society for Civil Engineers code ASE 7-16. So we have actually have a quite good code. We have updated regularly our code for our building codes so that we have the latest code in our hand. Of course, always the problem is the implementation. We are now actually still disseminating this code, and I think it would take some time to actually deliver this to all over Indonesia, because Indonesia is a big country. And in this SNI, we have this updated earthquake hazard map. And as this is our code is based on ASCE 7-16, we adopted the 2,500 years return period earthquake acceleration, ground acceleration. So this is our map. This is our updated map in our 2019 SNI. And this actually was developed using the latest probabilistic seismic hazard analysis models and the latest ground motion models. So we have this a quite good earthquake hazard map actually. We do have also the SNI 2833 2016. This is the earthquake code for bridges. So we do have this as well, and we have this. We adopted mostly from Federal Highway Administration's manual. So we again adopted this from a U.S. code. And in this code, we have a different return period. In this code, we use about 1,000 year return period code. So we have a different peak ground acceleration compared to the national building codes. So, but we do have these codes in our hand, but again, we still have a big homework to actually disseminate these building codes to our public. And so at the general overview, we do have a good building codes actually, or structural codes for earthquake resistance design. And this is the underlying premise that we need to have when we talk about earthquake hazard mitigation. But if we look at the this map in a more detailed fashion, we still have a lot of homework to do. And when we talk about that map, we actually talk about what we have in for the site here. So what we have now is that we do have a good earthquake source maps. Our geoscientists have done a great job to develop the source maps. And I think this is due to the advances in BMKG stations. So we now have a better and better source maps. But when we talk about more detailed into this probabilistic seismic hazard analysis, we still have these challenges. When we talk about the ground motions, we talk about the path. And the models for that, the ground motion models, we still rely on ground motion models from abroad. We have very little knowledge about our specific ground motion models. And we haven't have the good grip on the how the layers, the soil layers would affect the seismic hazard as well as ground motion as well. So we do have a tremendous homework to do to better identify the path and the effect of the superficial layers to have a grip, a better and better seismic hazard map. And I'm going to continue with what we have done so far for the transient ground movement. We have actually started developing ground motion models since 2015. But at that time, we have not too many stations recording earthquake accelerations. So we have started developing some ground motion models in 2015. And we are, of course, not really satisfied with that, as the number of data is not that many, but we are still trying to develop more and more. And recently, we just developed this ground motion model for central Sulawesi region. So fortunately, BMKG was supported by Australian government to develop, to install some networks, accelerometers network and other instruments. And for a couple of years, we got quite many data actually, about more than 1,000 data. And we actually try to develop this ground motion model for the Sulawesi, central Sulawesi region. And we actually try to identify more detailed about the sources and the how the sources are different sources would develop different types of ground motions. But the problem is that we then understood that our data are not enough yet. So we couldn't actually develop a more detailed ground motion models, although we have quite a number of data. So we need to have more and more data. So fortunately, BMKG now is developing, installing more and more instruments. So hopefully we could get more data. And we have developed this simple ground motion model for this central Sulawesi region. From magnitude 2 up to 7, the database, as you may see before, is but up to 6 point something, 6.6. So this is what we have developed so far using this data. But again, we are not satisfied yet. We need to do more and more to refine our model to develop better ground motion models. For example, this slide shows the several models compared to the actual data, and we could see quite a significant scattered in our data. So we need a better model to capture the actual ground motions from earthquakes in central Sulawesi region. And we actually did also some analysis for the Lombok earthquake sequence, and this publication would come out I think late this year, and we look at the 5 major earthquakes in the Lombok earthquake sequence, and of course from the engineering perspective. And we look at the records from 2 particular stations, the MASIS stations and TWSI stations. We have seen quite interesting results from these stations. And what I would like to, what I would like to emphasize here is that the MASIS station is located south of Mount Rinjani, while the TWSI station is located on Sumbawa Island, not on Lombok Island. So it's a different island. And you may see that the geology of these islands are different. The TWSI station is located in a more older geologic formations, while the MASIS station is located as a younger one. And we could see that from the shear wave, the MASW measurements, that the shear wave velocity for the MASE is lower than that for the TWSI stations. But according our standards, the SNI 1726/2019, both stations are categorized as the SB site. So they are within the same site. But then we recognize that the behavior of the records are completely different, although they are within the same site class according our SNI. So we could see that the MASIS station has a lower frequency, predominant frequency, and the TWSI has a higher predominant frequency, which is expected based on the shear wave velocity. What I would like to emphasize is that the recordings tell us different things, and the MASIS stations, although MASIS station is typically was closer to the sources, compared to TWSI, but the accelerations in massive station is much lower than the TWSI. So this is quite surprising actually, and you could see in this figure, for example, the massive station acceleration could be only about 5% of the accelerations of the TWSI station. So it is quite surprising. And because when we talk about general attenuation behavior, the a shorter distance would have a higher acceleration, but it's not in this case. And we thought that the hypothesis is that the Mount Rinjani would provide some filtering for the massive stations, and we found that the trend of the data is quite surprising, as the massive station recorded a lower acceleration compared to the TWSI station. So what I'm trying to say here is that we have a lot of homework to be able to capture specific local mechanisms that would affect our ground motions. And we also develop a VS30 estimator. As you may know, that the BMKG has adopted a USGS shake map system. And this shake map system uses the VS30 site class based on the Dr. Wald's research. And what we have found in this research is that the estimator developed by Dr. Wald tends to overestimate the VS30 in Indonesia. We have done a lot of comparisons, and the general trend is that the general trend is that the Wald's equation is our system tends to overestimate. So we have developed VS30 estimator for different regions in Indonesia. In this particular example, we show the one for Padang, and we extend Dr. Wald's model with the elevation models and the geomorphology models. When we we used a lot of BMKG data, VS30 data, based on a geomorphology unit. And we then develop a more refined VS30 estimator for Padang and other places in Indonesia. So we managed to have a lower, a better equations as indicated by the median and the standard deviations. And we could compare the Wald's model on the left to our model on the right, and you could see that our model should give us a better VS30 estimation. This again to give us more refined ground motion models. And the Palu 2018 earthquake gave us a tremendous opportunity to learn about permanent ground deformations. And you may know that in Palu in 2018, we experienced a major lateral spreading and liquefactions. This is, and we know that in Palu, it was a near fault site. So there was a recording from a BMKG stations in Palu, and we could see that the peak ground accelerations is about 0.3 to 0.4 G. And we learned about the permanent ground deformations and all over Palu. We did collaborations with US GEAR of the United States. Geotechnical Extreme Event Reconnaissance is funded by NSF. And we focus on this village of Lolo village. And this could be, in this village, it's not a big village, but we could observe that there was a major ground deformations. And we could see this yellow block is it's actually a housing complex, and it moved partly about 120 meters. So we did some research here, or we are still doing this research, and this is the housing complex that was sheared off. And what we found that if we look at the international database, our lateral spreading in Palu is much higher compared to the lateral spreading in other places in the world. So it gave us a very tremendous opportunity to do research. So we have collaborations with researchers from Japan, from the US, to do some liquefaction research. And we now are doing research on lateral spreadings. We are now developing physical tests and numerical simulations to better capture this phenomena. Lastly, we just touch upon we just started structural foundations research. We do now right now is a physical test to do more on the structure side, not on the hazard side. Some physical research, and we do some numerical research to better capture the behavior of our Indonesian engineering practices, so that we could have a better mitigation for earthquake hazard in the future. So in the closing remarks, that we need to develop our Indonesia specific knowledge. This is very important. So we have a very specific models that we could capture our earthquake hazard better. And thanks to BMKG now, and we have more and more extensive monitoring. Hopefully that we could have more and more again. And of course, we invite for collaborations, national collaboration, international, so that we could have a better data with better Indonesian specific knowledge for our mitigation efforts in the future. And I think that ends our presentation.
Okay.
Thank you, Mr. Moderator.
Thank you, Professor Wijoyo. I think we come to the session of Dr. Karen. Please, your time, Dr. Karen. You might like to have about 15 to 20 minutes as well. Okay. Time is yours.
Okay, thank you. So first of all, I want to say thank you for the invitation to speak today. It's my pleasure to talk this morning. So I'm going to talk in a bit of detail about the Lombok earthquakes in 2018, because there were some quite unusual and puzzling earthquakes in many ways. And I think that they reveal some fundamental aspects about seismogenesis. So before I begin, I just want to acknowledge my collaborators in this project. So they're from the Earth Observatory of Singapore, which is where I am a postdoctoral research fellow, and also at BMKG, ITB in Bandung, and Peking University. Okay, so what controls the fundamental properties, such as location, size, and rupture process of large earthquakes? So this is a long-standing question within earth sciences that we've been trying to answer. And it seems like every so often there's a large earthquake that occurs, and it can shed some light on some aspect of the system. And the Lombok earthquakes were an example of an earthquake that does just that. So this morning, I'm going to start by giving a bit of context into the regional tectonics. Then I'm going to talk about the details of the earthquake sequence and what controlled the earthquake ruptures, and finish with some implications for tsunami hazard in the area. Okay, so Lombok is located next to Bali, just off the east coast of Java. It's part of what's known as the Lesser Sunda Islands. In the south, it's bounded by the Sunda megathrust. So this is the subduction zone where the Australian plate is subducting beneath the Sunda plate where Indonesia is. Okay, so it's a very seismically active area. All on this map on the right, all these circles are earthquakes. And so of course we have earthquakes associated with the subduction zone. But behind, so like on the other side of the volcanic arc, there are also a lot of earthquakes. So this is Lombok right here where this red star is. So if we look at the moment tensors of these earthquakes, we see that they're thrust earthquakes. And so the fault plane is striking east to west direction, and it's dipping to the south towards the megathrust. So these thrust earthquakes happen on what's known as the Flores thrust. This thrust was discovered in about the 80s from some seismic reflection data. So it frequently does rupture. The largest earthquake that we know about was a magnitude 7.9 earthquake that was just off the island of Flores, and that produced a tsunami in 1992. Okay, so one of the striking features about these islands is their volcanoes. So this is a map of Lombok itself on the left, and it's really dominated by this stratovolcano called Gunung Rinjani. So this is a huge isolated volcano that's still active today. And it was actually the site of the largest and the most explosive eruption in the Holocene, apparently with a 43-kilometer eruption column. And on the right are some images of Rinjani from this paper. And you can see that there's a big caldera at the top of Mount Rinjani, which is 6 kilometers wide. So this is a really a big feature. Okay, so coming on to what I want to speak about today, which is the earthquakes that hit Lombok in 2018. So these are some photos of some of the damage seen in Lombok. There was a lot of building damage, particularly in West Lombok. And I want to draw your attention in particular to this photograph in the middle. So this is from northwestern Lombok, and they saw that corals were actually uplifted in the earthquake. So they were uplifted above the high tide line. So it's showing that there's a significant amount of uplift in northern Lombok. Okay, so the earthquake sequence was unusual. So the whole sequence lasted about a month, basically in the month of August. So this is showing magnitude versus time here. So we look in detail at the sequence. The first earthquake happened at the very end of July, and that was the magnitude 6.4. And then on the 5th of August, so about 1 week later, there was a magnitude 6.9 earthquake. And that had its own aftershock sequence. And then 2 weeks after that, on the same day, there was a magnitude 6.2 earthquake in the morning, and then a magnitude 6.9 earthquake in the afternoon. So this is very unusual. Normally we would expect to see one large earthquake and then its aftershocks. But here we have 4 earthquakes larger than a magnitude 6 and 2 earthquakes of the same size. So yeah, quite puzzling. So after this first earthquake, a team from US and ITB traveled to Lombok, and they deployed a seismic array on the island. And that array was actually active just before that first 6.9 earthquake. So it recorded the whole earthquake sequence. So this is the local array that was deployed on Lombok. This is a photo of Muesli deploying one of these short period nodes, which we've now used a few times in aftershock studies, and they're very quick to deploy. So it seems to be very valuable for this situation. So this is Lombok, and the triangles are showing the locations of the local array that was deployed. And then we also use some permanent broadband stations, which are operated by BMKG. So they also provide some very valuable data. Okay, so what we did to analyze these earthquakes was to combine a lot of different types of data. So we used the local array in order to accurately relocate the seismicity. And then we also got focal mechanisms for all events larger than a magnitude 5, which is about 20 events. And we did that by inverting the waveforms for regional seismic stations. And we independently constrained the event depths for these large earthquakes. And we wanted to do that because the event depth is really important for this study, as you'll see a bit later on. So we got independent constraints on the event depths by looking at high frequency teleseismic waveforms that contain the depth phase, so it's very sensitive to the depth. And then we also inverted INSAR data with the seismic data in order to get finite fault slip models for the earthquakes larger than a magnitude of 6. Okay, so this is the details of the rupture sequence that we found. So I'm gonna just spend a bit of time talking through this figure on the right-hand side because there's quite a lot of information in it. Okay, so if we start with this map in the middle, so the circles are representing the hypocenters of the earthquakes. So the sequence started with a 6.4 earthquake, which is located here, if you can see my pointer. And this these orange contours are representing the coseismic slip of this event. And then the first 6.9 earthquake happened to the west, and it actually ruptured in this area here. So it ruptured in a westward direction. And you can see from the slip model here that there were actually multiple high slip patches. So this is showing that it ruptured multiple asperities. And then there was the 6.2 and the 6.9 earthquake. They were located in the east. We didn't get a slip model for the 6.2, but for the 6.9, we see that this ruptured to the east. It ruptured much deeper and had a very smooth and broad slip pattern. Okay, so the top panel here is just a timeline. So this is from July to September. So this is to say that this was the first 6.4 earthquake, then we had the 6.9 earthquake, and these are all of its aftershocks over to the west. And then the other 6.9 earthquakes here, and these are its aftershocks over to the east. So now if we think about the depth of these earthquakes, so the colors here are the hypocenter depths, and the bottom panel is a vertical cross section through the middle of Lombok, so through this AB line here. So if we look at this in some detail, we can see firstly that there's quite a continuous and narrow seismogenic zone, and that this seismogenic zone is shallowest in the middle of the island, which is nearest to Gunung Rinjani, and then it deepens onto the east and to the west side. So it's about 10 kilometers depth here, and then it deepens to, I think, 23 or so kilometers onto the western side. So this, yeah, is very unusual. And this clear arching pattern of the seismogenic zone, it raises some questions as to what has caused that. Okay, so what controls the depth and the width of the seismogenic zone? So there's a few factors that could be responsible for this. I'll just briefly talk about some of the background. So in order to think about this, we need to think about the strength profile in the crust and why earthquakes happen in the first place. So the upper part of the crust is frictional, so that when the rocks are sliding past each other, they deform in a brittle way, and that produces earthquakes. And then below certain depths, at high temperatures and high pressures, rocks deform in a plastic way or a ductile way, so they cannot host earthquakes. And that boundary is what's known as the brittle ductile boundary. So that forms the bottom of the seismogenic zone. And large earthquakes tend to rupture at the bottom of the seismogenic zone. We also see that there will be a shallow limit to the seismogenic zone, and that's seen because there's a lack of earthquakes in the very shallow crust globally. But exactly what controls that is a bit uncertain. Okay, so in Lombok, we were seeing this change in depth in the seismogenic zone. So that could be controlled by lithology, so a changing composition of the rocks. But we don't think that that is what's happening in Lombok because it's a small area. We expect the lithology to be the same. So it could be a temperature effect. So if it's a hotter area, then that brittle ductile boundary would happen at a shallower depth. And it could also be a structural effect. So past earthquakes, such as the Gorkha earthquake in Nepal in 2015, showed that structural changes along a fault plane can actually limit where the earthquakes ruptured. So I'm going to be addressing the last two of these points, starting with the structural aspect. So what we did was build a 3D geometric model of the fault plane. And so we used some seismic reflection data from just offshore to the north of Lombok. So this was data that was acquired by a company called Multi-Client Geophysical about 5 years ago. You can see some of a few lines here. So on the data, you can clearly see a dipping reflective surface here, which is dipping down to the south below Lombok. So we interpret this to be the fault itself. So we picked the fault on the seismic reflection lines, and then we used that with the seismicity, the relocated seismicity, and the fault planes from the focal mechanisms in order to build a geometric model of the fault. So these are some panels down here. So what we found was that the fault is pretty flat in the shallow part offshore, and then it changes and dips at an angle of about 25 degrees to the south. And so one of the important things here is how flat the fault plane is. So these lines are structure contours along the fault plane. So what you can see, given that these are quite straight lines, we're not seeing any significant structure on the fault plane itself. So that's not the reason that the seismogenic zone is being elevated. Okay, so if we don't think it's a structural effect, then that leaves us with a thermal effect, which is quite expected because, of course, there is this big volcano in the middle of Lombok. So we built a thermal model of the crust at Lombok. We did that by using some geothermal data from some regional geothermal data. So we found that Lombok is actually within a relatively cold geological terrain. So it's a sort of cold background geology. And then we use a heat source, assuming we have a point source at Rinjani's crater itself. And then we essentially use a half-space cooling model. So one of our assumptions that we have to make is that the base of the seismicity is marking the brittle ductile transition. And that's a temperature of 450 degrees C in feldspar rocks. So this value comes from experiments in laboratories, and we expect feldspar to be the composition in Lombok. So, okay, so this is our model of the Flores thrust at Lombok. So these are two cutaway sections through the middle of Lombok itself. So looking at the geometry, first of all, this is our fault plane, so it's relatively flat offshore, and then the fault is dipping below Lombok itself. So if we look at the thermal model, that's shown by the dashed lines here. So the base of the seismicity is set to 450 degrees C, so that that's not surprising. But what is really interesting is the fact that the top of the seismicity also seems to match an isotherm. So that's an isotherm of 250 degrees C, so that falls out quite naturally from the model. And that 250 degrees C is an interesting value because at that temperatures below 250 degrees C, clay minerals are stable in the fault plane, and clay minerals deform differently from the higher temperature minerals. This is not necessarily something new. It's an idea that's been around for many years. But now with experimental data, we can see that this 250 degrees isotherm seems to be an important value within faults for changing the deformation style from maybe creeping by clay minerals in shallow parts of the fault to brittle deformation in the seismogenic zone. Okay, so I want to talk a little bit about tsunamis. So I'm just going to summarize the earthquake observations at this point. So we find that the upper limit of seismogenesis is also controlled by temperature, which is probably related to the stability of clay minerals. We find that the seismogenic zone was shallower and thinner near to the volcano where it's hot. So the first magnitude 6.2 earthquake actually ruptured the shallowest part of the seismogenic zone, and then the later magnitude 6.9 events ruptured in either direction along the fault plane. Okay, and I've not gone into this in much detail, but we saw that the differences in the rupture styles between the 6.9 events is probably a reflection of the fact that the first 6.9 event was rupturing a shallower part of the crust, which has more asperities than the second event, which ruptured a deeper part of the crust and likely a more longer-lived fault zone. Okay, so I'm conscious of time, so I'm going to move on to spending just a few minutes talking about the tsunami hazard. So we've looked at the tsunami hazard in the western extension of the Flores thrust. So this is going towards Bali. So there were a few reasons we wanted to look at that. One is that historical earthquakes seem to be quite similar to the earthquakes at Lombok. So these are moment tensors from some events, and they're also occurring at similar depths. So we think the geometry of the fault would be quite similar. And then, of course, this is, I think it's called the Lombok Strait between Bali and Lombok. So the fault here is submerged, and rupture could have implications for tsunamis. And of course, the coastal areas of Bali and Lombok are highly populated. These are the two capital cities, Denpasar and Mataram. Okay, so this is an overview of the tsunami modeling.
Mm-hmm.
So essentially, we put a fault plane in here where this white arrows are. Our fault has got the same geometry as what we obtained in Lombok. So we have a fault dipping to the south, and that rolls over.
Could you make it shorter?
Yeah, I can make it shorter. Okay, so rupture of this fault here is increasing or affecting the seabed, and that's causing some displacement of the sea surface. So we model different scenarios this one is probably the most likely scenario. To cut a long story short, the capital cities are prone to some high tsunami waves, depending on the scenario that's modeled. And particularly Mataram, the first tsunami wave might arrive within 15 minutes of the earthquake rupture. Okay, so this is my conclusions. I wanted to make 3 points, if I may. One is that the unique location of Lombok is really important to show us this temperature change and how temperature controls seismogenesis. The second is that the rapid deployment of the seismometers to record the aftershocks was really, really valuable in this case. The data was really important. And then the third point is the Flores thrust does pose a tsunami hazard and should be studied further. Okay, thanks very much.
Okay, thank you. Previously I prefer to have first session and second session, but in fact, all those 4 speakers would be similarly talking about the structure and also meldings. So I can go through to the second session, that is Professor Walter Moni. Mas Angga, could you share the biodata of Walter Moni? Professor Walter Moni is from USGS. We can see the short biodata of him. And perhaps the second speakers would be Dr. Supriyanto Rohadi. He's from BMKG. Supriyanto, and he's from BMKG. He's a researcher and graduated from ITB. Okay, perhaps you might like to share about the presentation of Professor Walter, Mas Angga.
Okay, so
please, your time. Yes, yeah, your time, Prof. Please.
We'll have discussion later then.
Yes, discussion later.
Oh, okay. Oh, I know what I did. I need to go to the beginning. Okay.
Right.
So, salam alaikum.
Walaikum salam.
Nice to be here and to see a lot of old friends. The previous 2 talks were outstanding. I was really sitting on the edge of my chair to hear. I'm going to talk about earthquake and tsunami hazards in Indonesia. And by now this figure looks a bit familiar because Dr. Karen Litkow and others have shown similar maps. Very seismically active area with a lot of damaging earthquakes. The Lombok sequence is on this slide. And I would like to point out some things about what you see here. First of all, the earthquakes are distributed everywhere and show many different focal mechanisms. That is to say, strike slip faults, normal faults, thrust faults. Normal faults can be seen in the outer rise, thrusting at the trenches. But I have some news for everyone. The fault map, which is on the screen together with the bathymetry and focal mechanisms, is the standard Peter Bird from University of California, Los Angeles fault map. And this is the most commonly accepted map for the world, plate boundary map for the world. And in my opinion, it's wrong. So we have the wrong idea of the tectonics of Eastern Indonesia if we go to this American fault map. For example, this offshore fault to the west of Sulawesi, I believe, does not even exist. It's imaginary. There is no evidence for it in the seismic data. And the fault to the south of Timor, shown here with this certain pattern, is labeled as a crustal fault, whereas it's very clear that there's an active subduction zone there. And I think we just saw that there's quite active underthrusting under Flores Basin. My message for everyone working in Indonesia is that you need to challenge the assumptions regarding the geology, tectonics, geotechnical data, earthquake data, everything about your country. As Dr. Prakoso said, you need Indonesian specific knowledge. And the current state of knowledge of many things in Indonesia is ripe for revision. Okay, so that's my first point, that we really need to reassess and reevaluate what we think we know about Indonesian geology, tectonics, hazards, and everything. Here are 16 tsunamigenic earthquakes, just 16 examples in the last 20 years. And you can see again, they're very well distributed. Some are coming from the Banda Sea, some are in the Malacca Sea. And today I'll talk a little bit about work that my colleagues and I have done and people from around the world in the area of Palu. Here USGS has begun to make a different plate boundary map. We haven't finished yet, but now we have subduction in the Banda Sea rather than what was shown by others, and we show underthrusting in Flores. We are working with our colleagues at BMKG to try to understand what's the true tectonic setting of your country. And now let's look a little bit about what happened in Palu. This is a slide from the Journal of Geophysical Research by Suplaveda, excuse me. He's also got this Makassar offshore trench. As I'm claiming here, this is doesn't exist. It's complete error. It's been propagated through the scientific literature, but I cannot go into that too long. And then the Palu Koru fault is postulated to take this kind of a trend. As everyone knows perfectly well, the Palu earthquake did not occur north of Palu City. It didn't slip on this fault here, and it was located far to the east. Here are four possible geometries that are discussed by a number of authors. One is that the Palu fault is in the west side of Palu City, passes beneath the bay and connects up to where it's seen on shore on the east. Then there's a jog in model 2, model 4 is here, and the model 3 in this paper is to assume that the original fault was responsible. Let me just clarify for everyone that there are two pieces of evidence that indicate that the fault must have been located over here north of Palu. Well, I said two, there are many more than two. The earthquake teleseismic location, the local location, the INSAR data that shows the offset on the east side of the bay, and finally, the geoscientists in the BMKG in Palu City actually walked out the fault and identified the trace on the ground. So there is strong factual data that tell us exactly where this offset is. And we, as far as I know, I don't know if anyone can prove to me that this Palu Koro fault really exists at all. I don't know what the evidence for that is. Maybe that's wrong as well. Okay, the Palu event is quite unique because it had a non-seismogenic source, a strike slip event, and it passed through the southern Palu Bay. Here's a time, this is a complicated diagram. The earthquake epicenter is here up to the north, about 80 kilometers north of Palu City. And the coloration here shows the time. The time history of the rupture is very important. This is the energy release versus time. And the peak energy release was at about 20 seconds. Since this earthquake ruptured at a speed of 4 kilometers per second, it was very fast. the biggest release of energy was actually at Palu City. So there were two high points, one north of Palu and the one correlating with Palu City. This is an important diagram for everyone to examine and to try to understand. What we're looking at is the fault plane. The viewer is located to the east and we're looking to the west. The hypocenter is located here and the rupture propagated simultaneously to the north, as shown here, and also to the south, shallowing as it moved, as it ruptured. As we just said, it took about 20 seconds for the earthquake rupture to reach Palu Basin with the high slip. So it's a bi-directional rupture. But what I'd like to emphasize to you is that the strongest rupture, I shouldn't say strongest rupture, the maximum amount of slip, the largest slip and the largest energy release from the Palu earthquake was in Palu City, not to the north. This is very common. Many earthquakes are nucleate at depth. A typical depth would be 16 to 20 kilometers near the brittle ductile transition. They commonly do rupture towards the surface, and the maximum slip is not at the hypocenter. The maximum slip is not uncommonly spaced away from that. So it's no surprise that there was strong liquefaction in the city, in and around the city of Palu, because that's where the really strong energy release was, and the soil was violently shaken and liquefied. So the Palu earthquake may have had a epicenter 80 kilometers to the north of the city, but where the action really was, where the strong slip occurred, was partially beneath Palu Bay and certainly beneath the city of Palu, Palu Basin. Listed on here are features which are called asperity 4, 3, 2, and 1. And asperity refers to a strong point on a fault zone or a strong patch. And the authors here have identified these four separate zones. Asperity 3 is what caused most of the damage, knocking down buildings and causing liquefaction. Asperities 2 and 3 would have contributed greatly to the tsunami. So what caused the Palu tsunami? Was it the seismic deformation beneath the bay, or was it shaking that induced landsliding? There are so far 18 papers written about the Palu tsunami source. These papers are published in leading journals such as Geophysical Research Letters, Geophysical Journal International, Seismological Research Letters. There's a lot of discussion, and each paper has something to contribute. Here's a timeline evolution of the literature on the Palu earthquake. The earthquake occurred. Indonesian scientists and their colleagues immediately got to the field for field studies. Field studies are in black. Tsunami modeling is in red. And you can see that so far, there have been 18 publications in the period of about 16 months. Well, let's see. No, it's 2 years now. Today is 2 years because it's nearly the anniversary. I'm sure there'll be 18 more papers. So what can we say about the origin of the Palu tsunami? Among the data that can be used are INSAR to locate the fault. Very important are video-derived time histories because there were not a lot of seismometers present, and the tide gauge data. There was one tide gauge record within Palu Bay. So one idea is that the fault ruptured and moved The bathymetry, uneven bathymetry in the subsurface would have caused the water to displace. The displaced water comes back down to equilibrium due to gravitational forces, and this would generate a tsunami. So how does that model do in explaining the Palu tsunami? Here are the four models fault models I described earlier on the west side of the fault, and this is on the east side of the fault. So what are we talking about? Very important step was that people went to the field after the Palu earthquake and tsunami and actually measured the wave, the run-up heights of the tsunami inundation. So we have data here, which is the observed run-up height. That's the height that the water level reaches at its maximum distance of inundation. And we have a computer modeling based on that fault geometry. So we have critically important field data, which are compared with computer data. The fault model does not fit the data. The authors, Sepulveda, are unable to find any fault model that will yield these kind of very high inundation, run-up values as high as about 9 meters, 9 or 10 meters. So displacement beneath Palu Bay played a minor role, maybe some role, but it was a minor role compared to what many of you have perhaps heard about, was local coastal subsidence and subsurface landsliding. So here are 15 landslide sources which are have been considered. I traveled to Palu 2 times and I went to some of these sites. You can go to a village and find that about 100 or 200 meters of the village has disappeared into Palu Bay. That is to say, coastal subsidence. There is no question about this. This is very clearly happened. It's photographed by this airplane source. It's evident from satellite data, and you can visit and talk to the local residents who will confirm the magnitude of the coastal subsidence. We're talking about volumes on the order of a cubic kilometer. When these kind of sources are included into the calculation, you can see that we have a very good agreement between model calculation with these multiple sources and field observation of the tsunami run-up. So this is a real success story, and it required careful field operation combined with enhanced modeling of the entire process. That is to say, considering the subsurface bathymetry as well as the physics of landsliding. So in conclusion, co-seismic deformation played only a minor role in generating the Palu tsunami. This is in contrast to the co-seismic deformation, which causes all of the tsunami energy for most subduction zone tsunamis. And several landslides in Palu Bay were the major contributors to the tsunamis. If I had more time, it would be very interesting to talk about the generating causes of the liquefaction and landsliding in Palu, which are also related to this very strong earthquake, and particularly to the strong slip that occurred on the west side of Palu City. So this conference is about the cutting edge of hazards and earthquake and tsunami research. And I'll end by saying that the big challenge, I think, for us is to understand the 19% of those tsunamis that have an infrequent source, Sure, 81% are due to subduction zone earthquakes, pure and simple. But 6% are due to earthquake-generated landslides. And this could have happened, for example, at the Lombok sequence. Those earthquakes could have generated strong landslides and a very strong tsunami. Volcanic eruptions are 5%, and everyone knows Anuak Krakatau that claimed many lives in December of 2018. 4% are pure landslides, which are not generated by earthquakes, and even 4% are unknown sources. It's nice to have this kind of a meeting, which is very international, because as you can see from this map, tsunami sources are international as well. Indonesia has plenty, but there are many others that are distributed around Indonesia, which are well recorded with tide gauges, seismometers, INSAR, and other data. And it's putting it all together that will make a difference. So that was a very short presentation, but that's part of the cutting edge. Thank you.
Thank you. Thank you very much, Prof. I think we go through the Dr. Supriyanto. Your time is yours. Please share, Mas Angga.
Thank you, Prof.
Okay.
I will share my...
Oh, you have your slide already. Okay, good, thanks.
Yes, thank you. I'm sorry I turned off my video because of the internet traffic.
Okay. Please. By the way, during your preparation, I think all the speakers can see the question and answer on section. Okay, please, your time, Supriyanto. Mas Angga, what happened with the sound?
Your voice check in your share screen not
Yeah, Mas Supriyanto.
let me check this.
Still unmute, perhaps. It's not working for the voice. Please check.
Pak Supri, we have not heard your voice.
The speaker is not working. No, we cannot listen. Mas Angga, can you check that?
Halo.
It's to work. Should be working.
Di sebelah mana mungkin?
I think just share your screen and
Excuse me.
Can you solve the problems, Mas Angga?
Yes, yes, please wait.
Please share it. Even you can share for Supriyanto's slide from your side.
Excuse me.
Yes, yes, please, Mas.
Aduh.
No, it's not working.
Yes, yes.
Just do live, Pak.
Do
Yeah,
live.
it
You
is
just tell
easier
us.
maybe. Yeah.
Okay, a moment.
Okay, you skip some part.
Hello?
Yes, please. You come up with your main ideas. Yeah.
Okay, I'm sorry because of my technical problem. Might be I repeat my presentation.
Just straight to the main ideas.
Okay.
Run out of time.
Yeah. Okay. This is the feature of the p-value map that indicate of the high stress in some region in Indonesia. For example, in West Padang, in West Lampung, in south of West Java, in south of East Java, in Sumba, in Pandasi, in Maluku Sea, and also in some region in Papua. This is the density map. The p-value map is also depend on the density of the earthquake. So have high density of earthquake will give the good resolution of p-value map. This is the This is identify a seismic gap from the moment release data until 2018. We identify 5 zones of seismic gap in around Indonesia, especially in Sunda Arts, such as in West Padang, the Sunda Strait, in the south of the East Java, and also in south of Bali, and also around the Flores. We're also conducting research about radar monitoring to monitor the radon anomaly because of the before the earthquake occurred. We have 2 sites of the radon observation. one in Tadulako University, and one in Palolo. It's about 71 kilometers from the epicenter of the earthquake. This is the result of the monitoring radon observation. This shows that increasing radar anomaly before the Palu earthquake since August 13, 2018, and also water level anomaly before this earthquake. This is the zoom version of the figure. The anomaly increased since 11 August or 13 August. Based on tsunami hazard map, we also conducting research about the radar monitoring. As we know that in south of the Java, Central Java is prone of tsunami hazard. So BMKG collaboration with the MIC Japan install one couple of radar, one in Parangtritis, Bantul, and one in Purworejo. We use the radio frequency 16 MHz, so we can reach in distance of 80 kilometers. This is the performance or the feature of the operation monitor for the processing the data and then create the dissemination information to give warning of a tsunami. This is the scheme or the block diagram of the radar tsunami radar from the observation of the data of the oceanic wave, processing, dissemination instrument to give warning to the public. But until now, the system is under testing, under validation. And after we finish the validation, we can use the information from the tsunami warning. In agency, I also conduct research about microsonation. We use two methods here. First one is horizontal vertical spectral ratio, and second one is multi-channel analysis of surface wave. From the spectral ratio, we identify the dominant period of the soil. So we can determine the site class of the soil. For example, if there is a low dominant period, it means associated with soft soil. If there is a high predominant period, it associated with hard rock. For the multi-channel analysis of surface wave, we create the source using sledgehammer to create the Rayleigh wave. From the Rayleigh wave, we can have the dispersion curve. And in version of the dispersion curve, we can have the velocity structure. This is the instrument that we use in the field. There is seismograph short period to monitor the ambient noise data. We already conduct the microsonation in some area in Indonesia. For example, in Padang, Sukabumi, Tasikmalaya, Cilacap, Kulon Progo, and Bantul. This is the map, for example, of the dominant period. From this map, we know that the red area have high dominant period. It's mean soft soil, and the green one is the low dominant period. It's associated with hard rock. And this is map of the VS30. The green is high velocity, and the red one is the low velocity. We also conduct microsonation after the big earthquake. For example, after the Palu earthquake, we conduct the microsonation and make the map of the dominant period. And we compare the map with the intensity map. So we identify in the area that have low velocity predominant, have big damage of earthquake shaking. For example, in Balaroa region. We also conduct inversion for the tomography. We have a research of ambient noise tomography and also delay time tomography. In ambient noise tomography, it is almost similar with the multi-channel analysis practice. If we have the source and we have two location of station, we have two stations, we can cross correlation between two stations to have the green function. The green function is the source of, it is as a relief wave. So we can have dispersion curve from the green function. And after we get the dispersion curve, we can inverse to have the velocity structure. This is the distribution of the noise is also influence of the green function. If homogeneous distribution, we have the symmetrical green function. If we have no homogeneous distribution, we don't have the symmetrical green function. This is the example of the result of our study in ambient noise in Sumatra for period 3 seconds. This is the Sumatra fault zone. In this map, it clearly identifies the basin in Sumatra. On the right side, we have map of the RIPET between each station. In delay time tomography, we conduct inversion from the location in Sunda Strait. We inversion the arrival time of the earthquake, travel time of the earthquake in the Sunda Strait region. We use the double different tomography. After inversion, we have the image of the tomogram, we call tomogram, distribution of the velocity structure. And we can also have the cross-section of velocity structure. From the cross-section, we clearly identify low velocity zone beneath the Krakatau volcano. My conclusion, just potential of the research collaboration in the future. I didn't make the conclusion about our research, but what we need in the future in a collaboration research. The first is earthquake monitoring system. Second one, developing earthquake or tsunami early warning. And then identify seismic active zone and create seismic detail hazard map, tomography of subduction zone and local fault zone. Maybe also identify slow slip event, deep earthquake, and also ground motion prediction equation, and other so many topic of the research collaboration that we have. Thank you.
Okay, thank you, Dr. Supriyanto. I think it would be interesting discussion that we can have. Probably all the distinguished speakers could see the Q&A on the list. Well, basically, several participants would asked about the sharing of the materials. Probably Mas Angga can help as long as they have some connection with the internet or something, email address, so you can share. But all the questions are very relevant to all the speakers. And probably I started with Professor Wijoyo to make some response coming from the questions. Please, Professor Wijoyo, your time is yours.
Yeah, thank you, Professor Koster.
Yes, please.
Yeah, I think there is a question about the geophysical data that I have to admit that I'm not a geophysicist, so honestly I cannot answer that in a very well way. So, but the main point I'm trying to convey is that the although our building code has specified certain values, and for this and for that, we have to remember that we are dealing with nature. So the uncertainty is always high. So that's the main main message. So we need to do more and more research and to be able to reduce that uncertainty so that we could predict the hazard better in the future. The second one is that about the locations of our accelegraph network. I and a BMKG staff and I have discussed this many times that we have to place the accelerographs in a strategic manner, meaning that we have to identify the potential seismic sources, and then we put most of the network in those locations so that we could get better results. For example, in Central Sulawesi, we BMKG have placed many stations there, although it's not that as dense as would be expected, but still we get better and better data. That actually shows that the locations of the instruments are critical to be able to develop better seismic hazard maps. And I think that those are the two questions that I've noticed so far. Thank you.
Okay, thank you, Prof. Dr. Karen, you have some response coming from the participants? Please welcome all your response.
Hi, thank you. Sorry, thank you for all the questions. I've tried to answer the questions in the text of the Q&A box. I can just talk about a couple of the questions maybe. So one of them was about the Rinjani volcano and the fact that there was no significant increase in activity of the volcano after the earthquakes. So yeah, I don't have an answer for that question actually, but it's intriguing. There was one small earthquake, which was a normal faulting earthquake near the volcano, I think about 6 months later, but apart from that, I'm not aware of any other activity on the volcano. Yeah.
Okay. Well, thank you, Dr. Karen. Professor Walter, please, you have some response concerning all the questions related to your area?
Okay, I'm looking to see which one I should reply to.
I think the first one in Tua, Pak Samsia asked about every 8 days there is a tremor, or something like regularly 8 days. And then he asked about the situation, why it happens.
So there's a period, every 8 days there is another earthquake. Well, I'm surprised because earthquakes don't have a schedule, and It would be very surprising if a regular schedule could be maintained. We saw a very nice time plot that Karen showed for the Lombok earthquakes. And one time there was a 6.2, then the 6.9 came after, let's say, 10 days. But the next sequence was closer. It's quite irregular. Do you remember the pattern, Karen? How?
Yes.
Yeah. So I don't believe that earthquakes occur with a reliable
Regular.
cyclical pattern. It could be chance. Then I see there was another question. What is the anomaly phenomenon of Palu's earthquake that caused the hazard can't be predicted earlier? Okay, so my answer to that is very clear. It's bad news. I'm sorry, but we haven't solved the problem of earthquake prediction. We haven't found a reliable anomaly that will proceed systematically earthquake prediction, an earthquake, excuse me. I'll give you an example. For large earthquakes, only 1 out of 20 have a foreshock, have a clear foreshock. Actually, Palu had a foreshock. It had a magnitude 6, 3 hours before the main shock, and people were dealing with that magnitude 6 when the larger earthquake occurred. But statistically, only 1 out of 20 has a clear, strong foreshock. So 95% of the time, we don't see that. If there was any warning for Palu, it would have been the magnitude 6, which would have raised the stress on the fault. So Palu, if anything, at least it had a foreshock 3 hours before. Is there another question? I think there was one about liquefaction.
Liquefaction, yeah.
I'm trying to find it.
We cannot predict the mega thrust, but at least we know we can learn from the the trend or things like the early warning or things.
So the question from Rudy Arif Satiro, what is the cause of liquefaction that happened in Palu when the earthquake occurred, whether due to earth shifting or due to landslide? Okay, the cause of the liquefaction in Palu had to do with shallow water table, a susceptible soil type, and very important, a long duration of shaking. I showed the duration diagram, the shaking had a duration of at least 40 seconds, and with the high duration, it will make an important difference. Secondly, I showed on the fault rupture diagram that the biggest slip, the strongest slip, was right there in Palu City, and the Balarora liquefaction site is right on top of the fault, just to the west of the fault. The other two are about 4 to 6 kilometers away. So Palu liquefaction was caused by shallow water table, high susceptibility, and an earthquake which was very effective in generating liquefaction because of its amplitude and duration. Thank you.
Okay, thank you very much.
Only questions for me.
Yeah, okay. Thank you, Prof. Untuk Pak Suprianto, barangkali bisa menjawab. Perhaps you can answer the questions coming from Central Java concerning the detection for mitigations. How long the detection national team concerning the earthquake?
Okay, thank you, Prof. And question from Amalia. Okay, from
Central Java.
I'm little confused about the question. The question is if the determination of the hypocenter, for example, or when the earthquake will occur. If the question is the hypocenter location determination, PMKG can determine the hypocenter in 3 until 5 minutes. Yeah.
5 minutes earlier, or you mean 5 minutes
after
earlier?
The earthquake
Oh, after.
Yeah.
After. Okay. So, is there any trending? Is there any indication beforehand, that is before it happens? Let's say 5 or 10 minutes before, that is trembling around or tremor around the area.
Yeah.
Let's say about 10 kilometers or something. What do you have in mind?
The question is the earthquake can be predicted? Almost all of seismology answer no, or
No.
not yet. Yeah.
Not yet.
Might be next year, might be 10 years, and might be not forever, I think.
Okay.
It is about earthquake prediction. But
what kind of indication concerning early warning system, the one that BMKG put on shore or something like that?
Okay, talk about the tsunami warning. We have the characteristic of the earthquake that generate tsunami or not. For example, first one, the hypocenter is on the sea. The magnitude more than 7, the less than 10 kilometers. And then we can release the possibility of the tsunami warning. And also the focal mechanism of the earthquake source.
Okay, that's interesting. Okay, I think all the questions have been answered, and probably Mas Angga can share the materials to all the persons and participants who asked the slides or something. As long as
I have one question for Dr. Lithgow. I think you can read it there.
Okay.
Or I can.
Okay, you can spell out. Yes, please, Doctor.
Okay, I just see, according to your results, the area of the potential rupture is very limited in depth. Therefore, there can never be a very strong earthquake because the fault surface area is too limited. Also, the tsunami hazard is low. Is that right? It's true, the fault surface area seems to be limited. So I guess this is kind of hinging on the fact that the shallow, there seems to be a shallow limit to the ruptures. And so I think that's a really outstanding question as to whether, if in this series of earthquakes we didn't see any shallow rupture, is that going to be the case in the future too? And I wouldn't like to say that that is the case or not. I would say that it seems like there would be a change probably in like the deformation style. So maybe if there's clay minerals present, they'd more deform by creep. So it's possible that that could rupture if there was higher stressing rates or higher loading rates. So there may be like dynamic ruptures or something.
Okay.
If it was.
All right.
So I wouldn't like to bet on it.
Okay.
You would not discount the possibility that it could rupture at above 20 kilometers, thereby making it a much larger event with the tsunami potential, with the high tsunami. Okay.
Exactly. I think the other thing is from the seismic reflection data, we actually could see down to about 7 or 8 kilometers on the fault. And there we see above the fault plane, there's a lot of folding. So it seems more like the compression is being taken up in folding rather than maybe in faulting. And also we don't see the fault coming up to the surface. It's kind of buried under sediment. So I think all that evidence does point to the fact that the shallow part doesn't rupture. But I think we would need more work to be confident.
By the way, do we have time for one more question? Or
yes, please. Welcome.
The general geometry that you have described at Lombok doesn't fit plate tectonics. According to plate tectonics, you have subduction and you have an overlying plate and a volcanic arc, but you have this back thrust, you have this other thrusting. In plate tectonics, we normally think that you have subduction and that's the main fault. And where did this other fault come from that is?
Yeah, thanks for the observation. So I was quite intrigued by this. So it seems to be because of the subduction. So we have the Australian plate, which is subducting to the north, and over to the east, it's actually continental crust, which is trying to subduct. So at Lombok is oceanic crust, which seems to be subducting quite easily, but over to the east, like I guess like Timor area, it becomes continental crust. And so that has a really difficult time subducting because it's so buoyant. And so then the compression seems to be taken up in the back thrust. I think it's called the Wetar thrust. And north of that is oceanic crust, which seems like it can subduct. So it's actually the compression is changing from the megathrust to this back arc thrust. And it's the continuation of that back arc thrust all the way over to Bali that is where we're seeing these back arc thrusting earthquakes.
Okay.
So yeah, I'm not sure that there are many back arc thrust earthquakes in the world, really. I'm not familiar with any other cases, but maybe there are some.
My experience is that everything in Indonesia is unique and different. You have to expect the unexpected.
Yeah, it's definitely a very a unique place, I would say, and I think it's really important that we understand the system because it can tell us a lot about earthquakes and plate tectonics.
I agree. I agree.
Okay, I agree with you. Okay, last question, perhaps from Ibu Amalia to Dr. Supriyanto. Is it possible Jakarta has having a problems of tsunami like Aceh? That's the question.
Yeah.
Supriyanto,
Thank you for the question. Jakarta located opposite with a subduction zone. So maybe Jakarta can little monitoring or observe the tsunami come from the Sunda Strait, but
so
not so high, I think. Yeah.
Yeah. Indirect
but,
effect of
yeah,
the
not
thrust.
Impossible. Let's say impossible tsunami generate from the north
of Jakarta.
Yeah.
Yeah, yeah.
Okay.
So yeah, I can see from your map that it's on the south of West Java. That would be possibly the thrust itself.
Yeah, yeah.
So Jakarta would be on the north side of the West Java. So it's almost impossible. But the indirect effect would be possible.
Yeah, yeah. Right.
Yeah, okay.
Indirect.
Okay. That's okay. I think it's about time to finish our session here. And we come back to the MC. Please, Mbak Sulis. Thank you very much for the distinguished speakers. I think I appreciate so much about your presentations and also the answer all the questions. Thank you.
Thank you.
Yeah. I think if there are any questions that have not been answered yet, we will send the question to the panelists and we'll get the answer to you through email. Thank you.
Yeah, yeah. Still some question, I think.
Okay, take a picture first for all the speakers, distinguished speakers, please. Mas Angga, open your video.
Okay.
And all the team.
Thank you.
Thank you.
Thank you.
Thank you very much.
Thank you, Prof. Joyo.
Thank you, everyone.
Thank you very much.
I leave you out.
Thank you Thank you, everyone.
Thank you, Mbak Neri.
Thank you, Pak.
For the useful conference.
Thank you, Professor Raldi, for leading the
Thank
session.
you, Mbak Sulis. Yeah.
Yes. We just got the sad news that the director of School of Environmental Science, Dr. Emil Budianto, passed away this morning.
Passed away.
Yes.
Oh,
so
we'd better take a pray. We'd better take a pray together. take 1
yes,
minute
Pak.
to have pray
Yes.
for him. We start with Al-Fatihah for Muslim, and the rest would be adjustable. Okay, thank you very much for the news and for the sad news. I believe we condolence to the family left. Thank you, Mbak.
Thank you. And this event about to come to the very end. I hope you found the presentation of this symposium are informative and helpful. Please accept our forgiveness if there is which shortly means please forgive us for shortcoming. Thank you very much for all speaker, Professor Wijoyo, Mr. Walter Muni, Dr. Karen Litku, Mrs. Nelly, Florida, Dr. Supriyanto Rohadi, and all participants. And see you in the next symposium. Thank you.
Thank you.
Thank you. Bye-bye.
Bye-bye,
Thank
everyone.
you.
Thank you,
Bye.
everyone. Thank you, Pak Wijoyo, Pak Walter, Bu Karen, Pak Raldi. Thank you very much.